Wait, what were you saying, Amelia?
This is like a big deal to me. Like we're giving like a conference presentation. I'm like
Yeah.
I know.
pretty rad.
Hello, my name is Stephanie Luedtke, and I will be introducing our project, our analysis of the shifts in alpha carbon backbone within X-ray structures of human acetylcholine esterases. The acetylcholine esterase molecules that will be analyzed were covalently bound, thus inhibited by a unique series of organophospharamides given the name Novichokes. Before we continue on to our analysis, I would like to provide some background information surrounding Novichokes and why they are one of our main focuses today. So we'll start with what are Novichokes, how they have come to be relevant, and how do Novichokes compare to other nerve agents. The mechanism at which they inhibit the active center gorge starts with the serine 203 portion of the catalytic triad in that center gorge. The hydroxyl group attached to the serine compound acts as a nucleophile as it attacks the phosphate group present in the Novichok backbone, right here presented by A234, which thus pushes electrons onto the fluorine, which is a great leaving group. This leaves the acetyl pocket completely filled with the inhibitor itself, thus making it very difficult for antidotes to come in and attack the oxygen in this red corner over here. The name Novichok encompasses a variety of potent nerve agents that were refined and improved over time. They were developed back in the 1970s to 1980s under the classified program Foliant. However, they weren't widely known until the early 1990s, revealed by a former member of the institute at which they were made, Dr. Vil Marizano, after coming to the United States, who was shown in the right corner of the slide. His book, State Secrets, as seen here under his image, was published in 2007, which revealed the synthesis of Novichok and how dangerous it could be to the public. In October of 2019, Novichokes were added to the list of toxic chemicals under the Chemical Weapons Convention of 1997, which placed strict guidelines and controls specified within that treaty. Fairly recently, 6 inhibitors that were classified as Novichokes are approved by all member countries of the OPCW, which is stated here on this slide. You can find it online under Schedule 1, A column, toxic chemicals. 3 Novichokes that were added to the list, A230, A232, and A234, are the most notable due to their presence in recent poisoning attacks of prominent figures, which I'll cover shortly. A230 and A232, A234 are characterized by their similar composition, however, they're distinguished by their unique properties. Attached to phosphate group 4 of the inhibitor, A230 has a methyl group. A232 has a methoxy group, and A234 is just like A232, except it has an ethyl group where a methyl would be. One of the earliest high-profile cases began in Salisbury, UK. Sergei Skripal, a former Russian military intelligence officer, and his daughter Yulia Skripal, as seen here by these images, were found unconscious on a bench in UK near a shopping center. They were later found to be poisoned with A234, what we just covered in the last slide. They lived, however, their poisoning was followed by a lot of speculation, thus launching Novichokes into the conversation for not only reporters and journalists, but for researchers as well. Earlier this year, on August 20th, well-known Vladimir Putin critic Alexei Navalny was also poisoned with the already infamous Novichok nerve agent, verified by German, Swedish, and French scientists, revealed by Angela Merkel. He fell ill on a flight traveling from Tomsk to Moscow and was immediately flown to Berlin shortly after the plane had an emergency landing. Most recently, it was confirmed that traces of the nerve agent were found in his hotel room in Tomsk, inciting more speculation of the origins of that Novichok presence in Europe. Like any other nerve agent, Novichok's covalently bind to human acetylcholinesterase, inhibiting acetylcholine breakdown. Excessive ACH leads to the overstimulation of muscarinic and nicotinic receptors, which ultimately causes neurological and physiological deterioration. They are also thought to block cholinergic neurotransmission in the peripheral and central nervous system. Novichoks differ from other nerve agents in their toxicity levels. A230, in A230, I believe, A234 is 5 to 8 times more toxic than BX neurotoxin. And A232 is 10 times more toxic than Soma, which makes it have a high risk factor if attacked than other nerve agents. What's unique about Novichoks is the stability level of the compounds in multiple states. Novichoks can exist in a solid or liquid state, allowing them to come in contact with a potential target through their skin, which would be absorbed into the system and thus metabolized, inhaled, or ingested. The purpose of our study is to analyze the effect of Novichok on the structure of human acetylcholine esterases. We will do this by analyzing the protein backbone domains as well as the acetyl protein loop of an inhibited acetylcholine esterase molecule for conformations that deviate away from its non-inhibited original structure. We also aim to analyze backbone conformations that were influenced from antidotes, especially HI6, to analyze the level of potency that auxins have on reversing the unique and challenging effects that Novichoks bring upon binding. During our analysis, we primarily utilized 2 internet programs, as seen here, named PACT and NANO. PACT, or Pairwise Alpha Carbon Comparison Tool, is a reference point-based application that overlays 2 PDP files, liganded and non-liganded enzyme conformations. Using this, we are able to quickly analyze before and after binding conformations that are influenced by Novichoks. Nano, the program that we are in right now, is a virtual reality workspace that allows for the analysis of PDB files and results that are produced from PACT. Here are my sources, and I will continue on to analyze the first molecule conformation comparison. Hello again. Here we have a molecule of inhibited acetylcholine esterase by Novichok A230 overlaid with its non-inhibited counterpart. Up here, the graphs, we have a representation produced by PACT of the inhibited enzyme and the uninhibited enzyme chain A, indicated conformations with its gray peaks. Greatest change is highlighted with the yellow bars. And right below, we have the inhibited enzyme against its own chain A and chain B, again indicated. The parts of greatest change between the two indicated with the yellow highlighted bars, which correspond with the yellow counterparts on this molecule right here. So if I were to, I will display the surface, but before I do, I'm going to indicate that the yellow conformation changes are inside and outside around the acyl pocket, and closest to the van der Waal represented molecule, where I'm circling right now, which is the A230 inhibitor, are alpha helix chains. As you can see, let me pull this up. Closest to you is the active center gorge, where it has the inhibitor nestled in there and is shown to fit to size with its van der Waal molecule representation.
Right, and so the largest change is right at the top of the opening, as you mentioned, alpha helical parts that form one of the walls of the gorge. It is not actually acyl pocket, but it is close to the acyl pocket and towards dimerization interface of the enzyme. Okay, thank you, Stephanie.
Thank you. Hello. As you can see, right here we have an acetylcholine esterase molecule that is inhibited with A234, right here, that is shown all to the right on a slide. So this is chain A of the acetylcholine esterase molecule, which is represented on the bottom of this graph right here. And it is compared against its chain B counterpart, which is shown in the orange right here. As you can see, there's little to no difference between the two chains, which is underneath 0.3 angstroms. However, when we compare the inhibited enzyme against its native counterpart, we are shown to have a lot of difference between these reference points, which is represented by the yellow highlighted sections on the molecule itself. If I zoom in here, as you can see, the inhibitor A234 is represented by the van der Waal representation of the molecule, which is in the center, and the yellow parts are surrounding the active center gorge, specifically around areas 330 to 380, which I will emphasize right here, which is facing towards you. The bottom yellow highlighted part is closest to the acyl pocket, which is important for the binding of ACH.
And immediately underneath the inhibitor that you are showing now, the alpha helical part. Yeah. Okay. Very good. Thank you, Stephanie.
Thank you.
Go.
Hello, everyone. My name is Bianca Pomar, and I will be presenting on this Novichok over here, A234, and comparing it to peroxone, which is a known pesticide. Earlier, Stephanie mentioned that this molecule right here, A234, is a Novichok, and it reacts with the human acetylcholine with the Novichok over here. What happens is it performs in an SN2 fashion, and this fluorine group on the A234 will leave, and it'll go ahead and bind on the acyl pocket side. This +1 charge, and also the fact that within the acetylcholine esterase, glutamate right here, or glue 202, which is right next to the active serine, it goes ahead and forms an electrostatic attraction, which goes ahead and moves not every single, but a lot of electrons within this molecule over. And it forms an attraction over there, which leaves it open for the acyl pocket for this Novichok A234 to come in and attach. Comparing to peroxome, what happens over on that side is this molecule is far too large for it to go ahead and attach the acyl pocket. And as you can see, there is no +1 nitrogen charge. So what happens is it distorts the acyl pocket, making it unable to fit and inhibiting our acetylcholine esterase. Over here, we compared the two on this graph. It demonstrates each peak demonstrates where it differs on the chain between the two structures. So you could disregard all the red structures, all the red arrows, because those are all breaks or end terminals where there's obviously a lot of distortion. The green arrows are where we want to pay attention to, because that is where it signals the most distortion between the two chains, the alpha carbon chains. We figured this out by using the PACT program mentioned earlier, and it shows 4 different peaks, with the most important being at the 290 to 298 range. What this graph demonstrates is the fact that there is a big distinction between peroxone and A234, even though, as you saw earlier, they're very similar molecules. And it does this primarily through an SN2 fashion, as mentioned earlier. The biggest peak right here can be demonstrated on this molecule, where we presented an overlay of the two molecules. I have highlighted here in yellow, this yellow ribbon chain right here, where the 290 and 298 region is. And as you can see, they both don't overlap completely. And the gray and pink areas, a lot of them do overlap, which is why there isn't that many peaks, and there's only 4 green peaks as to where most distortion occurs. The pink ribbon represents the human acetylcholine esterase, and the gray ribbon represents the distortion that occurs when the molecules bind.
Peroxone.
Where peroxone binds. My apologies. And I think that's it. I don't know what else to say now.
So the reason for absence of distortion of acyl pocket that we're looking at now in Novichok inhibited enzyme is that it phosphorus, due to that electrostatic attraction, is shifted to the right, and there is no pressure to acyl pocket, and it assumes the same conformation as found in native enzymes. So even though it's a larger molecule than peroxone, it does not distort acyl pocket. So that's the finding from this comparative analysis. Okay, very good. Thank you, Bianca.
Thank you.
Okay.
Oh my gosh.
Hello, everyone. My name is Emilio Luna. I looked at the human acetylcholinesterase bound to the A234 Novichok nerve agent inhibitor. And you can see both on this diagram and on this protein structure, the A234 inhibitor can be seen here, displayed by van der Waals structure, just to make it a little easier to see. and it serves as a covalent conjugate and is bound to the active serine site of the acetylcholinesterase. And these orange arrows can be seen when looking at the B chain of the structure. It's not letting me make it bigger. Here. It can be seen at these orange highlighted areas of the structure, which tell us that there has been a small change in the backbone there are small structural differences between the A chain and the B chain, but one important thing to note is that these changes are actually on the outside, on the surface of the structure. So we can say that the changes in the structure did not occur because of this A234 inhibitor. Now, when we look at the A chain and B chain of the acetylcholinesterase bound to A234 versus that same structure, but now with the presence of the HI6 antidote, which can be seen here. This is this HI6 antidote. Which can also be seen here on this diagram. We can see that now there are actually significant changes in the carbon backbone of the protein structure, which are displayed here by these green arrows on this diagram and can be seen by this yellow-green highlighted area on the protein structure. Now, something important to note is that these changes are actually, as you can see, around the area of the HI6 antidote. So you can see around the area of the HI6 antidote. So we can conclude that because of the introduction of the HI6 antidote, significant changes in the alpha carbon backbone occurred within this protein structure.
Whoa.
Hi everyone, my name is Celine Boho, and today for this presentation, I will be doing an analysis on one of the novichokes called A242. Since there's no X-ray structure available for A242, as well as the other two remaining novichokes, there are structures available for A230, A232, and A234. So we've decided to create a model of A242 based on A234 and the available structure. So as you can see here with this gray molecule, inside is the A234 molecule within the molecule acetylcholinesterase, and you can see that with the gray. And so we've taken this original structure and we have turned it into A242 and have created accommodations with the enzyme here. So now we're gonna overlay A242 on top of it so you can clearly see the differences between the two novichokes and how they conform differently to the molecule. And so I'll do that right now. So as you can see, despite being an overlay, you can see how there is a difference between the two molecules and how they are positioned within acetylcholinesterase. And so now we will display the surface so you can clearly see how it fits within the active center and their overlaps. So currently you're looking at the active site of acetylcholinesterase, and that's what makes it accessible for these novichokes to enter into the enzyme. And you can clearly see that overlap over here that we saw previously.
Hello everyone, my name is Yunshen Li. Today I'm going to compare the A234 template with the new model that I created using Nano. Here we have the A234 template, as you can see, as mentioned by Stephanie and Celine before. And this is the new model that I created using Nano. As you can see here, I added like 4 different carbon chain on the template. And this is what it looks like in the Nano, the 3D model of the new model. And this is the packed analysis comparing the new model inhibited acetylchlorine esterase against the A234 template inhibited acetylchlorine esterase. And as you can see here, there are 3 different peaks, and they are between 0.3 to and 0.4. So there's no relatively small differences. And here, as we can see, as indicated, those 3 differences as indicated here in the yellow parts, 1, 2, 3. And this is a representation for the overlay between the new model inhibited and the A234 template inhibited acetylcholin esterase. And this is the, and as we can see here, this is the version after we added the surface. And if I can move this closer to the camera, you can see here, the new model can enter the active gorge with no problem. I did 4 times the minimization, so the whole enzyme kind of relax around the inhibited ligand, and yeah. So the conclusion would be there's no big difference in protein structure after adding the carbon chain, which means forming the new model.
Okay, excellent. Thank you very much, Yunshen.
Thank you, Professor. Thank you, everyone.
I think it's
Yeah, I said that. At times, like I've noticed that professors will like record, and sometimes it'll give like an option to like record the audio or like share the audio, and sometimes that may factor in what is recorded.
Okay, I have here audio only. Let's see. So it looks like I have video without audio.
Oh no.